This presentation will cover a study done on the Thai Power Development Plan published in 2015 by the Thai Ministry of Energy. This study uses various modeling software to project regional emissions data based on the Power Development Plan between the years 2016 and 2036. To the left, you can observe a legend that you can follow throughout the whole presentation. This will let you know where in the presentation we are, but more importantly, it will follow the exact same progression of the study itself, so you can follow it step by step. We'll start with a methodology, which will give you an outline of how the study was done. We begin with an in-depth analysis of the Thai Power Development Plan itself. Using that and other resources, we collected fuel share data for the entire nation. We then developed different scenarios for each of our atmospheric models, and then were able to compare results of each scenario for each model. We will culminate at the end of the presentation with our conclusions and potential need for future study. The Power Development Plan 2015 is a document that was published by the Thailand Ministry of Energy. It provides the growth of the energy generating sector of Thailand from the current status to 2036. It incorporates fuel consumption, efficiency measures, power plant openings and closings, and transition system improvements. Highlighted in the PDP are changes in the overall fuel share, going from being dominated by natural gas to a more even split between coal and natural gas. This is, in part, to achieve three main goals set forth in the introduction. The first, to increase the energy security of the nation and reduce single fuel dependency. The second, to maintain a reasonable cost of energy for the consumers, and third, to reduce greenhouse gas emissions from the power plant sector. This chart, taken from the PDP, compares the current PDP 2015 with an older version drafted in 2010. The 2010 version of the PDP estimated larger energy uses up until 2036. The 2015 revision, however, sees much lower estimates for all years of the PDP's lifespan. As you can see, by the year 2036, there will be about a 15% decrease in the total energy uses between the two power plants. Much of this comes from the energy efficiency measures and the focus on renewable energy the current PDP has adopted. This chart represents the breakdown of Thailand's final energy capacity in 2036 once the 2015 PDP has reached its fruition. During the time of the PDP's installment, you can see that Thailand begins with 38,000 megawatt capacity, with an additional 57,000 megawatts being added and 25,000 megawatts being retired between 2015 and 2036. There will be a net increase of about 32,000 megawatts, bringing Thailand's total capacity up to 70,000 megawatts. Let's take a second to look specifically at the new capacity during the PDP's installment and where that capacity is going to come from. This chart specifically shows the breakdown of the new capacity to be installed between 2016 and 2036. Approximately 35% will come from renewables, whether they are domestic or purchased from neighboring countries. However, the main focus of this paper is on the projected increases in coal usage during this time period. Highlighted in red above is the additional coal capacity slated to be installed, 7,500 megawatts. Much of this project was concerned with the effects of this specific increase that would cause effects that would be most noticeable. The first model used to begin projecting emissions and atmospheric quality was the Greenhouse Gas Interactions and Synergies, or GAINS model. The GAINS model takes in data for each pollution-producing sector and generates projected emissions in a given time period. The first step in GAINS is compiling a list of all power plants in Thailand up to the present. From this, the raw fuel input data was generated. Using the projections in the PDP, the fuel data was extended to encompass 2016 to 2036. The data was then broken down by fuel type, power plant size, and power plant combustion technology to format it for inputting to the model. Then, the emission control scenarios had to be created. Using the Energy Technology Perspectives 2012, a document published in the International Energy Agency, and the data from the TCAP Eclipse project conducted in Thailand in 2010, two scenarios were created, CLE and MRF. CLE means current legislation of emission technologies, and MRF means maximum feasible reduction. These will be described in further detail ahead. The next step was to take all the data formatted for the model and upload them for emissions calculations. With fuel data and control scenarios for every 5-year interval between 2016 and 2036, the model was run and data was collected. The data collected was emissions outputs for the entire nation. It includes many species of pollutants, including greenhouse gases, NOx, SOx, PM2.5, PM10, and several others. These were then used as inputs for the CAMX model. The GAINS model splits Thailand into 5 regions in order to better handle emissions calculations. The regions, shown above, are the Bangkok Metropolitan Region, the Central Valley, the Northern Highlands, the Northeastern Plateau, and the Southern Peninsula. The 2 charts you are about to see give a summarized look at the changes in fuel share as well as an increasing consumption between 2016 and 2036. Here, you can see the current fuel consumption comparison by region, which is clearly dominated by natural gas, followed by large uses of biomass and renewables as well as coal. In 2036, however, you can see a notable increase in coal as well as substantial decreases in natural gas as per the PDP's projections. In total, an additional 1,300 petajoules are added. Notable changes associated with hard coal and brown coal include large increases in the Central Valley and the South as well as the Northern Highlands. The decreases in natural gas share are seen most in the Bangkok Metropolitan Region, and the large increase in biomass and renewables are mostly concentrated in the South and Central Valley regions. The scales on these 2 graphs were changed in order to better show the entire fuel share. In both, natural gas in the Central Valley is close to 1,000 petajoules and goes off the scale. As for 2036, the scale is different from 2016 because many fuels exceeded the 180 petajoule threshold. The fuel data was input to GAINS and run on 5-year intervals between 2016 and 2036. As was mentioned in a previous slide, GAINS takes emission control technologies into account for all contributing sectors. 2 distinct scenarios were developed with specific combinations of emission control technologies. One of these scenarios, the CLE, used emission controls based on current legislation projected until 2036, and was expected to see higher levels of emissions due to lack of any increased high-efficiency removal technologies. The alternate scenario, MFR, used the same set of emission controls as the CLE base case. Additions were made, however, to incorporate greater use of emission controls for nitrogen oxides, sulfur dioxide, and particulate matter, because they are significant hazards to human and environmental health. These extra controls were employed exclusively on coal power plants in order to focus on alleviating the emissions anticipated with the increase in coal use during the PDP's lifespan. The CLE used emission controls derived from the TCAP Eclipse project. These controls assume power plants would continue operations using control technologies based on current legislation goals and emission standards. Above is the current legislated expected use of some of the most efficient control technologies for nitrogen oxide, sulfur dioxide, and particulate matter, and as you can see, most are not planning on being implemented in the PDP's lifespan. Only electrostatic precipitators, or ESP1, are set at 100% penetration during any of these intervals. However, ESP2 represents a more efficient version of that technology, and coal plants would be better served using ESP2 or technologies like it to remove certain harmful pollutants. The MFR was created to project gradual yet aggressive implementation of the most efficient emission control technologies for coal power plants between 2016 and 2036. This table, which represents the exact inputs used to create this scenario, shows some of the same controls seen in the previous slide for the CLE. However, you can clearly see that these highly efficient technologies are not only all in use, but have heavily and promptly been implemented in the PDP's 20-year lifespan. This was done to observe potential reductions in hazardous emissions that are expected to come with the PDP's increase in coal usage. Later in this presentation, you will see a cost comparison that weighs the cost of implementing these effective technologies versus how many emissions they prevent compared to the CLE. 3 pollutants were analyzed from the GAINS output emission data. This graph displays nitrogen oxide emissions by GAINS region. The blue line represents the 2016 CLE, the red is the 2036 CLE, and the green is the 2036 MFR. Note that the power plant sector's emission is only one part of the total emissions. Levels of nitrogen oxide increased by a factor of 1.2 between the 2016 CLE and 2036 CLE scenarios, going from a total of 947 kilotons per year to 1,144 kilotons per year. 3 of the 5 regions showed an increased levels of nitrogen oxide emissions, with the BMR and Central Valley region showing a reduction. The Central Valley region's power plants equated to 19% of the Central Valley region's nitrogen oxide emissions. The drop in nitrogen oxide between the 2016 CLE and the 2036 CLE resulted from sectors like cement production and transportation using diesel combustion closing and being replaced by combined cycle and natural gas sectors. The region with the largest nitrogen oxide increase, the Northeastern Plateau, was forecasted to install one 105 petajoule lignite power plant in 2016 and 32 petajoules of biomass every 5 years, while uninstalling 20 petajoules of natural gas by 2026. The Northeastern Plateau region top 5 nitrogen oxide emitting sectors in both 2016 and 2036 CLE are transportation or diesel engine related. Sulfur dioxide emissions from all sectors in the CLE were higher than those of the MFR in 2036 by a factor of 1.2. However, the CLE 2036 sulfur dioxide power plant emissions were higher than that of the MFR 2036 by a factor of 1.9. Only one GAINS region, the Northern Highlands, exhibited a decrease in sulfur dioxide. This most likely results from retired coal plants, since a decrease from 160 petajoules to 102 petajoules was observed between 2016 and 2036. 2 regions, the Southern Peninsula and the Central Valley, responded favorably to the 2036 MFR scenario. The 2036 SO2 emissions were higher in the Southern Peninsula region than those of the 2036 MFR emissions by a factor of 8. The Northern Peninsula and BMR regions showed no change due to a lack of coal-fired power plants in the BMR and unchanging coal capacity in the Northeastern Plateau. PM10 emissions were higher in the CLE 2036 than in the MFR 2036 by a factor of 1.1. However, comparing only the power plant sector, CLE 2036 emissions were higher than the MFR 2036 by a factor of 2.8. Northern Highlands region had higher PM10 emissions than the MFR 2036 as opposed to the CLE 2036, most likely due to an absence of emission control technologies on biomass in the region. Additionally, the Central Valley region contributed 198 kilotons of PM10 in the CLE 2036 and 190 kilotons of PM10 in the MFR 2036. There was a small difference between the two. The Central Valley emissions commanded only small percentages, 8% and 4% respectively, of the total PM10 emissions. The main contributor to PM10 Central Valley emissions was the coal storage and handling sector built around the demand for added coal capacity in the Central Valley region. This sector contributed over half the PM10 emissions, 98 kilotons, in both 2036 scenarios. Now we're moving on to the CAMX model, which takes emissions outputs from GAINS and calculates pollutant concentrations in the air. There are a few key inputs, which are shown in green. One is obviously the emissions from the GAINS model. This includes emissions from power plants and other sectors like agriculture, industry, and transportation. Before the emissions data is loaded into the CAMX model, it first needs to be processed. During processing, the emissions from each GAINS region are allocated to point sources using special profiles created in GIS. The next input is initial and boundary conditions. Initial conditions dictate the concentrations of pollutants in the air before the model run begins, and the boundary conditions indicate the amount of pollutants flowing into Thailand from neighboring countries. The final input is meteorology data. This includes winds in 3 dimensions, sun intensity, cloud cover, and precipitation. The base data required to run CAMX was provided by another research group known as the TCAP Eclipse. They created a base scenario for the year 2010. This project updated the power plant emissions for 2016 and 2036, but left everything else the same for the sake of comparison. We assumed that there would be no change in temperature or weather because of climate change. CAMX processes the data into 4 to 6 minute intervals over the course of a model run, which was 1 month for this project. The output data is a binary file that must be processed in a Fortran compiler before finally viewing results. The resulting output gives projected hourly concentrations for each pollutant. Again, this project used all the same inputs as the TCAP Eclipse study, except for power plant gains emission data. Gains emissions were calculated in 5 regions, and not attached to power plant locations. Therefore, CAMX preprocessing requires spatial allocation to append emissions to a 12 km by 12 km grid. Emissions were allocated to power plant locations within each gridded cell proportionally by petajoule contribution of power plants with like fuel types in each region. The model uses chemical reaction solvers with data specific to hundreds of pollutants. The weather research and forecasting meteorological model was used to simulate hourly winds in 3 dimensions corresponding to the 12 km by 12 km grid. 2 sources used were the Megan-Mac database for biogenic emissions and the Global Fire Emissions database for biomass burning at each hour for each gridded cell. Because these 2 inputs relied heavily on meteorological conditions, their land-covered databases were merged with the WRF model predictions, notably radiation intensity and temperature estimates. Shipping projections were calculated from TCAP Eclipse survey data as well. CAMX post-processing simulates pollutant concentrations at known weather monitoring stations in Thailand. The simulated March and August concentrations in each 3 scenarios were averaged monthly. We chose these months because they corresponded to the dry season in March and the wet season in August. 7 stations were selected based on apparent changes, areas of high concentration, and locations with new installed capacity. 4 stations are located in the Central Valley region: Phra Nakhon Si Ayutthaya, Saraburi, Rayong, and Chonburi. 2 stations are located in the Northern Highland region, Lampang and Nakhon Sawan. 1 station, Surat Thani, is located in the Southern Peninsula region. For fair comparison, hourly pollutant concentrations were compiled into a monthly pollutant average for each station. 4 pollutants, nitrogen oxide, sulfur dioxide, PM10, and ozone, were analyzed. In this presentation, we chose to display nitrogen oxide and sulfur dioxide as they showed the most change of the 4. The first 4 power plants from the left are in the Central Valley region. Lampang and Nakhon Sawan are in the Northern Highland region, and Surat Thani is in the Southern Peninsula. The Rayong monitoring station measured the highest concentration of nitrogen oxide in the month of March for the CLE 2016. We noticed that the Rayong station had the highest concentration of nitrogen oxide because of the retirement of 2 pre-1990 coal plants and the replacement with largely natural gas-based capacity in the Rayong area. The rest of the stations measured no change in CLE 2036 to the MFR 2036 scenario. This is likely because of high additions of scattered biomass closer to the monitoring stations. For the Central Valley stations in August, we saw decreases in both 2036 scenarios except for Chonburi. The stations in the north and south increased in both 2036 scenarios, but were not different, likely due to scattered biomass in these regions. Rayong stood out again in sulfur dioxide concentration comparisons, much like nitrogen oxide in the month of March. It showed the largest decrease in emissions from CLE 2036 to MFR 2036. It also showed the only decrease between Rayong in 2016 and 2036. In the Southern Peninsula Gainers region, we saw virtually no change between the 2 2036 scenarios. However, we expected this region to follow the same trend. In 2019, a large coal power plant will be installed near Krabi. In the following 6 years, 2 more 1,000 megawatt coal plants will open in the Tepa and Songkhla province. The difference between emissions in the 2036 CLE scenario was greater by a factor of 8. It doesn't make sense for there to be no apparent difference between the two scenarios. We'll discuss this in further slides. As in March, we saw the same trends except for the Rayong 2016 CLE concentrations were below that of the Rayong 2036 CLE concentrations. Shown here is a cost comparison of the two emission control scenarios. The CLE, costing approximately $1.1 billion per year based on the 2016 dollar, represents an insignificant change from the present because this scenario maintains the status quo. The MFR, with effective reductions of several pollutants, costs $1.4 billion per year. Compared to the GDP of Thailand, which was $395 billion in 2015, this is not an outrageous cost, but it's also not insignificant. Given limited resource availability, different allocations of control strategies to regions where they are more effective would better utilize resources and help minimize costs. To determine the human health impacts of our CAMEX results, we used air quality standards from the World Health Organizations. Thailand does have its own set of air quality standards, but there are two main reasons why we went to the WHO instead. The first is that Thailand, from what we understand, is in the process of updating its air quality standards because they are out of date. The second is that the WHO guidelines are meant to be applied internationally, so we figured this would be the best option for our study. In the MFR scenario, health risks for all pollutants saw decreases, especially in areas close to power plants. The greatest improvements were seen in SO2. Also, PM10 emissions for power plants were overshadowed by emissions from biomass burning. This is the same graph displayed earlier in the presentation for SO2 emissions in March for all cases. The WHO standard is superimposed using a yellow line. It's worth noting that the only standard provided for SO2 by the WHO is daily, not monthly, and it's set at 20 micrograms of sulfur dioxide per cubic meter. This equates to roughly 7.6 parts per billion. While the WHO does not provide a monthly guideline, air quality standard concentrations generally decrease as time span increases. Therefore, 7.6 parts per billion is a conservative estimate for the monthly air quality standard. The greatest reduction in SO2 was seen in the Rayong monitoring station in the central Gaines region, and the MFR scenario reduced all human health risk in this area. It's worth noting that Rayong has high population density. Bringing SO2 pollutants to safe levels could benefit many people. Saraburi also experienced a notable drop in concentration in the MFR scenario. In August, the trend held through. Rayong experienced the greatest drop in concentration of SO2 between the CLE and MFR scenario. These maps display the emissions of SO2 in the CLE and MFR scenarios for March, and this helps explain why there was a drastic drop in concentration. Control technologies lowered emissions along that section of the coastline in eastern Thailand, which brought SO2 concentrations to a safe level in the model. Now, moving to particulate matter, these maps show areas of Thailand for both scenarios above the WHO monthly standard for PM10 concentrations. The sections shaded purple have unhealthy amounts of PM10 in the air, and you'll notice that there are some small differences, if any, between the images. Control technologies on power plants did not greatly change levels of PM10 because they were overshadowed by massive emissions from biomass burning in the north and central regions. Since there was much improvement, it's probably not worth buying costly PM10 emissions reduction for technology for coal power plants. To see the greatest reduction in particulate matter, it would probably be best to study the impact of control technology on biomass burning. As I just mentioned, the entire northeastern plateau and northern highlands had unsafe levels of PM10. Power plants in those two regions carried 70% of the share of PM10 power plant-related emissions in CLE 2036 for all of Thailand. Overall, biomass emissions dwarfed coal in these regions as well. Also, the southern peninsula did not witness much change in pollutant concentrations. We have two ideas for why we didn't see the change we expected in the southern peninsula Gaines region. One is that the winds in the meteorology scenario could carry emissions from the Krabi power plant away from the closest monitoring station in Surat Thani. The image in this slide shows a snapshot of the meteorology scenario. March winds blow across the south and would carry emissions out to sea. In August, wind patterns would push emissions south of the closest monitoring station as well. Also, the grid format of this model could dilute and mask the emissions from Krabi coal plant. CAMX is set up in 12 kilometer by 12 kilometer squares, and the Krabi plant is close to the coast. If the plant were in a square with water, the model would average the large emissions from the power plant with virtually no other sources. This would dilute emissions and mask the effects of the power plant. Either way, there needs to be further research into the impact of emissions from coal in southern Thailand. A necessary next step is figuring out why the South is not reflecting a difference in Gaines emissions from the expected coal power plants which will be installed in the future. One possible solution could be running a model with a better definition than a 12 kilometer by 12 kilometer grid. Developing a smaller grid would also be necessary for running BenMap. BenMap is a model that calculates daily from air pollution concentrations and would give more insight into how these emissions would impact human health. To optimize control technology scenarios, it would be best to add a mix of control technologies for different fuel types instead of just looking at coal. Another possibility could be reverse engineering our scenario development. Instead of targeting one fuel and analyzing its effect on air quality, we could change the fuel mix to attain optimal air quality. Additional economic analysis could also be done by comparing the cost of increasing emission removal technologies compared to the cost of healthcare in Thailand, as well as how many deaths could be abated by increases in pollution control measures. That concludes our presentation. Thank you for your attention. We greatly appreciate any feedback.